Question number 56. So we have been given 4 compounds and we have been given their pKs, and we have to arrange them in the decreasing order of their pK values. So again, if we look at the acidic strengths of these compounds, so we have phenol. Phenol is going to produce phenoxide ion as its conjugate base, and the phenoxide ion is resonance stabilized. And we can see that resonance occurs only in this molecule and not the rest. So obviously the acidity of phenol will be the most amongst these, and the pK value will be the least. So X is going to have the least pK value. And if we compare the others, we have been given methanol, we have been given water, and we have been given propanol. So students, we know that alcohols in general are more acidic than water because the conjugate base of water is OH minus and the conjugate base of other alcohols are OR minus. So if we talk about alcohols in general, the R, due to their exertion of a plus I effect, they are going to increase the charge density on this oxygen, and it is going to destabilize the negative charge, and hence the acidity of water should be greater. However, there is an exception of methanol. In case of methanol, we have CH3O minus. So this CH3O minus, although it has a plus I effect, but it will lead to increase in the negative charge density, which will in turn lead to increase in the extent of hydration. So what happened earlier was the charge density here was increased. So it had a greater feeling of being hydrated. But what happens is, due to presence of this R group, which creates steric repulsions, this alkoxide ion is not very much solvated. However, that is not the case with methanol. Due to a relatively smaller size of the methyl group attached, the solvation is still better as compared to the solvation of an OH minus ion in an aqueous solution. So students, we can see therefore that the acidity of methanol will be greater than water, and water will be greater than the other alcohols left. Okay, so if we try and arrange them in the order of their acidity, so the most acidic among the rest species will be Z, and its pKa will be the least among the other 3. So followed by water, water has a pK of Y, followed by propanol, which has a pK of W. So students, so the order of the pKa values which we are looking is correctly given in the option first. So we have to mark the first option as the answer to our question. Let us look at the next question now, question number 57. So we have to arrange the following in order of their ease of dehydrobromination. So the examiner is interested in the formation of alkene, and students, we know that wherever the formation of alkene is concerned, the stability of alkene is one of the major factors in deciding the major product. So if we look at the 4 options very carefully, if there is a dehydrohalogenation in the third compound, so we'll take out H from here and then we're taking out Br from here. So it will lead to aromatization of the compound. The third structure, when it undergoes dehydrobromination, it is going to give us benzene. So the third will be the most reactive among these compounds, followed by the second one. If we dehydrobrominate the second structure, we can have this H and Br leaving, and then there will be a double bond formation over here. So the second compound will lead to the formation of a conjugated alkene, which will again be stable because of resonance. So the second most reactive compound among the 4 given ones is the second structure. If we look at the first and the fourth option now, we know that the first option is a vinylic bromide, and vinylic bromide do not prefer to undergo elimination very easily because of the partial double bond character which is created due to resonance. Okay. So if we compare 1 and 4, 4 will undergo dehydrobromination very easily, forming a normal cyclohexene, whereas the dehydrobromination in the first compound will be quite difficult. So we have the ease of dehydrobromination as this. And if you look at the options, the correct order is given in the third option. Let us look at the next question, question number 58. So we have trans 2-methyl cyclopentanol, which is allowed to react with POCl3 pyridine, We have the second reaction in which cis-2-methyl-cyclopentanol is allowed to react with POCl3 pyridine. And the examiner is interested in knowing about the product, whether it is ZSEF product or Hoffman product, and the name of the major product form. So let us first look at what this POCl3 in pyridine does. So students, it causes dehydration via E2 mechanism, that is anti-periplanar beta elimination. Okay. So the H and the OH which have to leave should be anti to each other at the beta position. So let us try and draw the structure of the substrates given to us. In the first structure we have trans 2-methyl cyclopentanol. So we can have this structure. And if you look at the second structure, which is the cis 2-methyl cyclopentanol, we'll have the second structure is this. So now if we look at the possibility of a beta elimination, in the second structure, we can have this H and OH leaving together, which will lead to the formation of a more substituted alkene. However, if we look at the first structure, in the first structure, the OH and the H, which will lead to the formation of more substituted alkene, is not possible as it is not anti. So it is not anti. So this H will not leave. So in order for the elimination product to be formed, the POCl3 in pyridine will look for the other anti-beta hydrogen, so which will lead to the formation of anti-ZSEF compound or the Hoffman compound. So it is going to lead to the formation of this product. Okay, so this is our structure A and this is our structure B. Now let us check the options. Both reactions form 1-methyl-cyclopentene as major product. Student, this statement is incorrect. Only the second reaction forms 1-methyl-cyclopentene. So statement 1 is incorrect. Looking at the second statement, in both reactions ZSEF product is the major product. This is also incorrect. Only in the second reaction is the ZSEF product the major product. If you look at the third option now, only in reaction 1 ZSEF product is the major product. This is also incorrect. Only in reaction 2 is the ZSEF product formed. Looking at the fourth option now, A is 3-methyl-cyclopentene. Yes, students, this statement is correct. A is 3-methyl-cyclopentene. The numbering will start from here. 1, 2 and 3. This is 4 and this is 5. So there is an alkene present at the 1 carbon and there is a methyl present at the third carbon. So students, we have to mark the fourth option as the correct answer to our question. Let us look at question number 59 now. Consider the statement about the structure of nucleic acids. The unit formed by the attachment of base to sugar is called as nucleotide. This is incorrect, students. This is called as a nucleoside. Okay. Looking at the second option, nucleotide when linked with phosphoric acid gives nucleoside. The examiner seems to have reversed these species. The nucleoside, when it is linked to phosphoric acid, it forms phosphodiesterase, which is called as nucleotide. So the nucleoside and the nucleotide's position have been interchanged. Okay. So statement 2 is also incorrect. Looking at the third option, DNA has a double strand helix structure in which the strands are held together by hydrogen bond. Yes, this is correct. DNA has a double strand helix structure in which the strands are held together by hydrogen bond. So adenine is hydrogen bonded with thymine, whereas guanine is hydrogen bonded to cytosine. So the third statement is correct. If you look at the fourth option now, in RNA, adenine is bonded to thymine. This statement is incorrect, students. RNA does not have thymine at all. It has uracil instead. So looking at the options, we have to mark the correct statement. So the correct answer for question number 59 is option 3. Let us look at the next question. Question number 60. The set of product formed in the following reaction form a single isomer of optically active compound is. So we have been given a single isomer of an optically active compound. Okay. So it is allowed to react with NaOH-Br2 and then it is further acidified. Okay. So if we look at this reagent, it is going to give us a bromoform reaction. So bromoform reaction will happen from here and the carbon present over here will leave as CHBr3, whereas this will be converted into the carboxylate ion. So if I draw the structure of the chiral carbon, CH3, we have ET coming towards us, and then we have the carboxylate ion here. Now this basic medium is also going to hydrolyze this ester, so it will be converted into carboxylate as well. Okay. Now when this structure is acidified, there will be just simply addition of hydrogen on this O negatives, okay, and we'll have acids, okay, plus the CHBr3 which had left. Okay. So now the examiner is interested in knowing about the products in the product mixture. So we'll have a CHBr3 and then we'll have an optically active diacid. So it is to be noted here that the acid will be optically active because no change is taking place at the chiral carbon. The chiral carbon does not undergo any form of reaction, so the orientation which was before in the substrate would be retained in the product. So if the substrate was optically active, the product will also be optically active as no reaction is happening at the chiral carbon. So this will be an optically active acid. So if we look at the options, we can see that the correct statement is given in option 2, where it says that it forms CHBr3 and an optically active acid. So students, we have to mark option 2 as the correct answer to our question. This is it for today, guys. I hope the solutions were clear to you. Thank you.